Now we should be able to recognize ionic versus covalent bonds, but just putting them into those two categories is an oversimplification. Most real molecular bonds aren't purely covalent or purely ionic. They're actually somewhere in between those two extremes. The reason for this is due to a property of atoms called electronegativity. Electronegativity is a measure of the ability of an atom to attract electrons to itself when it makes a chemical bond. The higher its electronegativity, the stronger it pulls on those electrons, and ultimately the more time those electrons spend closer to that atom. If we look at this chart here, we can see that electronegativity increases as we move up and to the right, but that excludes the noble gases. The noble gases really don't participate in very much chemical bonding, and they have essentially negligible electronegativity. Fluorine is the most electronegative element. So if you just remember that, as you get further away from fluorine, the less electronegative the atoms become. Well, because these atoms pull electrons with different strengths, that means that when they form a bond, they don't share their electrons equally. So if we consider, for instance, HF, fluorine, we said, is the most electronegative atom. So he's going to pull on electrons much, much harder than hydrogen does. And that means the electrons are going to spend more time close to fluorine than they do next to hydrogen. And what this does is it causes a partial positive charge on the hydrogen and a partial negative charge on the fluorine. So we can show this in a couple of different ways. One is this arrow we use up here. The arrow points towards the side that the electrons are moving to. Fluorine is more electronegative, so it's going to point towards fluorine because that's where the electrons want to go. And then we put this little positive sign on the end to show that it's leaving behind a kind of positive charge on the hydrogen there. Another way we can represent that is with these little symbols here. That's the Greek symbol delta, and it basically just means small. So we have a small positive charge on hydrogen and a small negative charge on fluorine. This isn't like an ionic bond. The electron hasn't completely transferred from hydrogen to fluorine. It's just spending more time with fluorine. So it makes fluorine a little bit more negative, makes hydrogen a little bit more positive. When this happens, when you have this unequal sharing, this creates a dipole moment. Dipole moment, very simple, given by this equation down here, is a measure of separating positive and negative charge, a measure of how big that separation is. So if you have a positive charge and a negative charge, you measure the distance between them, that's R, and then you measure the difference in the charge, that's Q, you multiply them together and you get your dipole moment. That's usually measured in units of debye. We're not really going to calculate any dipole moments, but it's good to know what they mean, what it means when a molecule develops a dipole moment. And a dipole moment means that you have an unequal distribution of charge, and so we call this a polar bond, because if we look back up to HF here, that means you have a negative pole at your more electronegative element, and you have a positive pole at your less electronegative element. So now we see that it's not as simple as just covalent versus ionic bonds. Instead, we have kind of a continuum here. Down here is what we call a pure covalent bond. This would be if electrons were shared perfectly equally between your two atoms. And on this side, we have the ionic bond where the electron is transferred, and so you have two ions, a positive and a negative. Turns out a lot of covalent compounds are in this area here. This is a polar covalent bond. The electrons are still sharing, but they're being shared unequally. So the technical way to determine if you have a pure covalent bond or a polar covalent bond is to look at these electronegativity differences. So table 9.1 here shows you, depending on how big the electronegativity difference is, do you consider this covalent, a pure covalent bond, such as Cl2 here, a polar covalent bond, that would be this area in here that we had discussed, or an ionic bond, a pretty much complete charge separation. Now, I don't really believe in memorizing the electronegativities or the differences or anything like that, so I have a little bit of a simpler way of trying to identify the different bond types. First of all, ionic bonds are just the same before. Metal, nonmetal, polyatomic ion, things like that, that's an ionic bond, done. But now, if we have a covalent bond, we can do an extra step where we decide if it's a pure or nonpolar covalent bond, or if it's a polar covalent bond. But we're not going to do it by memorizing this chart here. I like to just remember two cases in which you have a nonpolar or pure covalent bond. If you have two of the same element, such as Cl2 or F2. Now fluorine here, he is the most electronegative element, but when you have two of them, they're equally as strong, so they must share equally. So if you ever have just more than one of the same element, that's going to be a nonpolar or pure covalent bond. The other one we can remember is whenever you have a carbon and hydrogen together. For instance, if I had CH4, that's only going to have nonpolar bonds in it because carbon and hydrogen together always forms a nonpolar bond. There's nothing really special about carbon and hydrogen. They just have very, very similar electronegativities. And the only reason I ask us to remember this particular example is because it shows up a lot in organic chemistry and biology. It's a very important combination. So that's the reason I ask us to remember this particular one. If I don't give you any other information, you have two different nonmetal atoms, they're not carbon and hydrogen, you can just assume it's polar. Most of the time, you're going to be right, and we're not going to worry about those exceptions. So, if we look at some examples here, decide if the bond that forms between each pair of atoms is nonpolar or pure covalent, polar covalent, or ionic. So we're going to start out the same way we did when deciding ionic versus covalent bonds. We're going to look at the types of atoms involved, and then if we have a covalent bond, we'll just do that one extra step. So we'll start with carbon and oxygen. These are both nonmetals, so it's going to be covalent, but it's not two of the special scenarios. It's not two of the same element, and it's not carbon together with hydrogen, so that means this is going to be a polar covalent bond. Really, really simple. Next one we have is sulfur and sulfur. Again, two nonmetals, so it's going to be covalent. But now it's two of the same element, so it's going to be non-polar. Right? It's one of those two scenarios I asked you to remember. Next one we have here is beryllium and nitrogen. Beryllium is a metal. Nitrogen is a nonmetal. So automatically we know that's ionic. We can stop there. Don't have to do anything else. Last example, we have carbon and hydrogen. Again, nonmetal and nonmetal, so we know it's covalent. And it's one of those two special scenarios I ask you to remember. It's a carbon and hydrogen combination, so it's going to be non-polar.